This week we'll talk about multiple continuous random variables. So we already talked about multiple random variables, multiple discrete random variables in section 2.2. And we already talked about continuous random variables in section 2.4, where we introduced integration as the new math machinery. Okay, so when we combine these two ideas, we end up with the concept of a joint probability density function. Okay, for regular random variables, single random variables, we can plot the probability density as a curve. When there are two random variables, the probability density looks like a surface. So the x and the y are the horizontal coordinates, and then the height of the probability density function is represented as the height of this curve. This is a view from above. The taller parts of the mountain, of the hill, are darker. So this is the area with most probability, and then it drops off to the sides. Okay, so this example, I don't show the code in the book, so you have to look at the notebook 25 multiple random variables. That's inside the notebooks folder. This notebook here. And using the multivariate normal from SciPy Stats, you can define this. What you see in the graph came from this distribution here. Okay, so what do we know about multiple random variables? We know they have, we know the axioms. These don't change, so probability density is always a non-negative function, and the total of the density integrated over the whole two-dimensional sample space must be 1. Okay, so these are the same, it's just double integrals. This is the example of a normal distribution. Disclaimer, don't worry about the formula. I need to give you some example, but ignore the complicated math. I just wanted to have a realistic example. So the bivariate normal distribution. Okay. Okay, so what do we know about multiple joint distributions is that we can factor out, so like this is the uncertainty in x and y, and if we say we don't know y, then we're integrating over y. What we have left is the uncertainty in x. Visually, this is the joint uncertainty in f of, right, the joint distribution. And if you compute the integrals along different y values, along different x values, so integrate over the y at 4, the density here is equal to the integral over all possible y values when x is equal to 4, and so on. So you see the density is like the marginal sums we did for tables of numbers, the marginal sums we did for discrete distributions. Here, the marginal is an integral. Okay. Of course, you can also do the marginals, integrate over the x's to get the marginal f of y. On the other hand, the conditional distribution, let's look at the picture, it corresponds to a slice. For example, here is the picture. This is the distribution if we cut it at different values of x. Okay, but you see that the total area here is not 1. So to make the slice into a distribution, we divide by the total area of this slice, and you end up with a distribution. So this is what the conditional looks like. Intuitively, so the vertical bar is red given. You already know about this. This distribution tells us the uncertainty in x if we know that the value of y was a particular value, y. So it's very different from the marginal, where we don't know what y is, so we average over all possible values of y. This one is we're zooming in. We're focusing on a particular value of y, let's say here. So it's the distribution, it's a slice. It's a renormalized slice. Again, continuing with the normal example. Chain rule, Bayes rule, we've already seen those before. Expectation, again, same thing as before. Some winning function times the density, but there are two integrals because it's a bivariate, it's a function of two random variables. The integral is double. I show an example with the normal. Correlation, we've seen that before. Covariance, we've seen that before. The expected value of the x minus its mean and y times y minus its mean. And the correlation, which is the normalized covariance. Independence, we've already discussed. So I'm intentionally repeating the ideas because it doesn't hurt to repeat some concepts. We're seeing things with continuous random variables. Hey, let's have a review. Otherwise, I would be like, hey, remember what we did? Like this, but some things are worth repeating. Okay, that's it. Exercises almost ready, and I'm gonna send them in a few hours. This is kind of two important examples. The average of n normals. Because this is foreshadowing for some things we'll study in section 2.8 when we talk about samples. But for now, it's just foreshadowing, just a cool result that the variance scales as 1 over n. Something interesting happening, but you don't know yet. It's a central result. No hints, no spoilers. All right. See you all next week.